Okay. So, as we said, there are some impracticality in Carnot cycle because we have the compressor and the turbine cannot handle mixture of liquid and vapor. So if we need to have a practical cycle, so we need to find a solution to this problem or to this impracticality. And this will happen by, if we have the refrigerant, so if we can vaporize it completely before the compressor, and if we can replace the turbine with another device that make expansion, but at the same time, this device can handle two phases, which is a throttling valve. So how can we overcome the problems or the limitations of using Carnot cycle in order to have a practical cycle? So again, you have two things. You have problem with 2 points, so you need to find a solution for each of these 2 points. So one of the points that about the inlet to the compressor, so in order to solve this problem, so we need to vaporize the refrigerant completely before going to the compressor. Another solution, we have a turbine, so the turbine cannot handle 2 phases, so we need to have another device, make the same function of the turbine, which is expansion, but this device can handle 2 phases, which is a throttling valve. So if we did this, we would obtain a cycle, and this cycle is called ideal vapor compression refrigerant cycle. This is an ideal practical cycle. So Carnot, this is ideal theoretical cycle, but this one here is ideal practical cycle. And this is how it looks like. So again, we have almost everything. We have the condenser, we have the compressor, we have evaporator or the boiler, but instead of the turbine, I have expansion valve. So I have this one, I replace, or this expansion valve, this is replacing the turbine. And if you want to see, so step number 1, 2, this is again isentropic compression. Step 2, 3, this constant pressure heat rejection. So again, if you remember, Carnot cycle was isothermal, but here, this one constant pressure, isobaric. Then we have step 3, 4. This is throttling expansion device, in which we have one of the advantage of using a throttling valve is that, let me just remove this so you can see it. One of the advantage of using this throttling valve is that it have constant enthalpy. So the inlet to the throttling valve and the outlet of the throttling valve, they have the same enthalpy. And this is very important to consider this. So when you replace the turbine with expansion valve, this gives you a device that can handle 2 phases. This is number 1. And even in the calculations, it saves 1 step in the calculation for you. Because one of the function of the throttling valve, the expansion happening at constant enthalpy. So enthalpy at 0.3 equal enthalpy at 0.4. So when you need to make the calculation to find the coefficient of performance, if you remember in power cycles, we found enthalpy at 1, 2, 3, 4. Here only you need 3 points, because already 3 and 4, they have the same enthalpy. And then we have the last step, constant pressure heat absorption and constant pressure. This means this step is isobaric. So the ideal refrigerant cycle, it has 4 steps, 1 isentropic, 1 at constant enthalpy, 2 isobaric. If you want to see the TS diagram for this cycle, so again, this is the first solution. So the inlet to the compressor, we need to vaporize it completely. So point 1, which is the inlet to the compressor, will be saturated vapor. Okay. Then we have isentropic compression to point number 2. Then we have the condenser in order to have saturated liquid. So if you have this step isentropic, so you will go from point 3 to point 4 dash. So this pass 3, 4 dash, if we have isentropic step. But because this pass, the throttling valve is at constant enthalpy, so this will be how it looks like 3, 4. So this pass 3, 4, this is represent constant H. So this is why it's inclined. It's not vertical, because vertical line, it means isentropic, okay, similar to 1, 2. Path 1, 2, this is isentropic. But 3, 4, it's not isentropic anymore. It operates at constant enthalpy, so this is why it's inclined. Clear? Is it clear why we have like the path 3, 4 instead of 3, 4 dash? Sure, sure. So if you need to find coefficient of performance for this cycle, so again, this will be based on if it's refrigerator or heat pump. So if it's refrigerator, so the coefficient of performance will be QL over the inlet work. And QL, this is H1 minus H4, because this is the path that's representing QL, low temperature heat transfer. Okay, and work in, this is H2 minus H1, because work in is on this path. If it's a heat pump, so now the objective is QH, so it will be H2 minus H3 divided by also H2 minus H1, the inlet work. Any questions?